Exponential growth and decay is a very, very brief topic. My plan is to spend 3-4 days on it because number one, all the questions you will face on this topic are very similar to each other. Okay, so unlike say, do you remember induction, right? Even though you have to go through the same steps, there are always different varieties of induction, which almost, apart from the actual method of induction, they don't share much to do with each other. Like you saw one, and if you see another one, which is a different style, you're almost not even sure where to start with it. There are all these little tricks like factorials and divisibility and trig and calculus. They're all really different, right? Exponential growth and decay, almost all the questions you look at, very, very similar. Just couched in different language, okay, words and that kind of thing. Secondly, you've got all the tools you need to do this topic already. In fact, I could almost just give you the questions. And in terms of differentiating, integrating, subbing in, doing problem solving, you guys can do it already. But I'm just going to walk you through the wording for these questions, and then I'm going to set you off on it and have a look at some harder examples later. Okay. So what's the idea of exponential growth and decay? Before we get to this idea, the exponential idea, right, I want to think about, okay, things that grow and things that shrink, okay, in nature. So in fact, sometimes this is not called exponential growth and decay. Sometimes it's called natural growth and decay. Some textbooks and some syllabuses call it that, okay? What are some things that get bigger and get smaller in nature, okay? Things like, say, the population of an animal, okay? Or a bacteria or something like that. Okay. Things like, say, a radioactive substance, which the idea of radioactivity is that it's giving off matter in the form of energy. Right? So as it's giving things off, that means itself it's getting smaller. Okay? So it's not getting bigger, it's decaying. Okay? The idea behind these things is that the bigger the thing is, okay, the faster it grows or decays. Does that make sense? I'm trying to get a really intuitive definition of this for you before I give you the technical one, because people see the technical one and they're like, I don't even know what it means. Okay? So the bigger something is, the faster it grows or decays. Okay, so let's think about populations, right? The bigger a population is, the more people within it can actually have children and that kind of thing. So the bigger the population gets, the faster it can grow. Does that make sense? And it starts off really, really slow.
Sorry,
come on in, that's okay. Starts off really slow. And then as the population gets larger, okay, that's why we've got this exponential shape. So that's why it's called exponential growth and decay sometimes. Okay? In the same way, the more of a radioactive substance you've got, okay, the more atoms there are that are giving off this radiation. Okay? More radiation means it's losing quantities of mass faster. Okay? The less there is, the slower it goes. So instead of this kind of scenario, you've got it doing this, and it's approaching some other kind of quantity down below here until it vanishes. Okay? So, the bigger something is, the faster it grows or decays. That's just the common sense definition. Here's a more technical one. Okay? The rate of change, so this is the growth or decay part, something's getting bigger or smaller. The rate of change is proportional to the quantity of whatever you have, okay? So if the quantity of a population is larger, okay, that means that the rate at which it's changing is proportionately larger, okay? So for instance, the idea is, if you got 10 people and that population is growing, okay, and you got 50 people and that population is also growing, we would say, you know, that the population of 50 is growing, not just growing, but it's growing 5 times faster than the population of 20. So there's this proportionality is here, okay? Alright, now, when you think about rates of change, okay, we're talking about differentiation, right? We're talking about derivatives. Okay? Whereas the quantity, what you've got, that's the original or the primitive function that you got your rate of change from, right? Okay. So we're saying that a derivative and its function are in proportion to each other. Okay? So how do we write proportionality? You've got two ways. You can say A, there's actually a symbol for proportionality. It looks kind of like an alpha. In fact, I write it like an alpha. When you typeset it, it looks slightly different, but anyway. You could say A is proportional to B. Okay? Right? Or if you remember, think back to year 10 and when we did variation as a topic. Okay? Direct variation, indirect variation. Rather than using this wiggly symbol, okay, this is actually equivalent to saying A is equal to KB. So A and B, they grow at the same rate or they shrink at the same rate, but there's this constant in here. Okay? Because it's the constant that tells you how much bigger or smaller one thing is than the other, we call it the constant of proportionality. Okay? So really this statement and this statement are equivalent. Okay? But in order to do calculus and that kind of thing, we're going to go with this one rather than this one. Okay? It just makes things easier to write. Now, one last thing. A and B here, okay? We said there are these two things that are proportional, okay? But we know what the two things are. They're an original function and what you get after you differentiate the function, okay? So let's try and take this, and rather than have A and B, which are general, they don't refer to anything specific, okay? How would we write them in terms of the language and the terminology we already know? Okay? We usually call functions like f, right? So you'd say f of x, well that'd be equal to the constant of proportionality multiplied by the derivative of the function. That's going to give you the rate of change. Okay? So you could write it like this, if you like. Okay? Sometimes we're going to call the functions f. Another common name for a function is like y, right? And y equals x, blah, blah, blah. So we could say y equals k y dash. Okay? Or k times that derivative. This should actually be a t. Okay? Because it's a rate of change over time. Yeah. Okay, now, think again, and I know the name of the topic sort of spoiled it, right? But what kind of function behaves like this? Right? What kind of function do you have when you differentiate it? You get something very similar, identical to it, but it's off by some kind of proportion, right? And the answer is an exponential function, hence the name of the topic. Okay? So what you'll find most commonly written is let y, or the other common name is p for population, okay? Let it equal a e to the kt. Okay? Now when you take the derivative of this, dy on dt, what's it equal to? Given that these two other letters, a and k, are just constants. T's our variable. What's the derivative?
K.
Okay, so this is an exponential, and it's a chain rule, right? So that k is going to come out the front, out of the, that's the inside function, and its derivative. And then the rest of it, it just stays the way it is, because that's what happens when you differentiate exponential functions. Okay? So you can see from this line here that it's obeying, we call it y. It's obeying this proportionality thing, right? It doesn't matter which side you've got the k on, that just means it's a constant. I can flip the constant over, it'd still be a constant, okay? But this idea here of that the rate of change and the quantity of what's changing, they're in proportion, okay? That's why the exponential function is the one we're dealing with, okay?